In the last class, we started with an 8086 instruction set. I will continue with that and we'll continue with data transfer instructions. We already had a look at the move instruction, exchange instruction, XLAT, push and pop. Today we'll see in-out instructions, LEA, LDS and LES instruction, and also the flag transfer instructions. Okay. Before I this is something which I missed out last time. So let me cover this first, and then I will talk about the in-out example. We have something known as segment override prefix. Okay, so generally when we write an move instructions, right? If I just write AX and within a square bracket BX, then the contents of the memory location which is given by, right? When I write within a square bracket bx, how is the physical memory location computed? From the ds register, okay, plus into 10, right, into 10 hexadecimal plus this contents of bx, right? And then the physical address gets computed. This is what we learned earlier, right? Whatever is the value here, right, in the bx register plus whatever is there in the ds register. Into 10 hexadecimal is nothing but placing these data of the ds registers, right, here out here with four zeros out here, right? This is if these are the 20 bits, so whatever is the contents of the ds register is placed here, right? And this 4 is 4 bits, the least significant 4 bits are kept empty, and then you add the contents of the bx and you generate the physical address, right? If I don't write this, right, so by default it will be taken as ds, right? But in many cases you want to specify rather than giving ds, suppose you have placed some data in the extra segment, okay? ds you generally write the codes and say some lookup tables and things like that, you have placed it in the es register, and now you want to access data from you have to access data the memory location and whose the first significant bits out here is given in the es register. Okay, so in the memory some locations, right, this is the memory, so some part of the memory is being accessed by ds, and now this memory, for these memory locations you have placed the right significant bits of those address in the es, right? So in that case I can write here es, okay, not only es, I can write ss, whatever. So accordingly so this is the known as segment override. So if I don't do segment override, the physical address will be computed by taking ds as the default segment register, right? And 4 zeros out here, so this becomes a 20 bit data, right? Contents of the ds in the most significant 16 bits of a 20 bit register out here, and the offset value will be taken from here, right? And then the physical address will be accordingly computed, and in 8086 we saw that the address lines is of 20 bits, so that's how the 20 bits comes out here, address bits comes here, right? This is ss, and then when we write this, this becomes the instead of the default ds register, now it becomes ss. Okay, let's let me explain you one example and also the machine code for that, then things will be very clear, right? Now suppose I write this instruction, right, move ds, that means this is segment override, right, 2 3 4 5 and bp, right? That means this is going to be the ds register here. Okay, so obviously in this particular example, even if I don't write a ds, it will take value as DS. Okay, so but then I have just written a DS. This could be anything, right? It could be ES, CS or SS also, right? For DS I need not write this. Okay, it will be taken as default. So but for this example I've just written here DS. Okay, so I could write ES, CS or SS also out here, right? Accordingly the address will be computed. So whatever is the contents of the DX register, obviously this is an 16-bit data because it is DX, that needs to be put into a memory location whose address is to be computed like from here, right? So this is the offset. Now what is the value of the offset? So this DS value gets here, and this offset value, that will be 2345 plus the contents of a BP register, right? So that is what will be done. So how to write the machine code for that? So whenever a segment override is to be given, whenever we do that, what is done is, so whatever is the contents of, finally what happens, whatever is the contents of DX register will be put into some memory location. And what would be the address of that memory location? DS into 10 hexadecimal, right? DS into 10 hexadecimal is nothing but inserting 4 zeros here. Okay, this is the 16-bit DS, inserting 4 zeros here. Okay, plus 2345, right, plus the contents of BP. So there could be some contents which is there in the BP which you have initially placed. Okay, so that address would be computed, and in that memory location the contents of DX will be transferred. So now coming to the opcode. So see, the opcode format is like this, right? Whenever you want to write segment override, these first three are fixed, okay, and these three are also fixed, right? So the segment override is an 8-bit data. It is this is the opcode for the move instruction, normal move instruction. This is the segment override. So this segment override is an 8-bit information which comes which is given as a prefix to the actual code. So whenever the microprocessor decodes and it encounters this particular code, it understands, okay, there is a segment override. Okay, now which is the segment override? So these 001 and first 3 bits and the last 3 bits are fixed. The middle 2 bits, okay, 00 stands for ES, 01 stands for the control segment, stack segment, and the data segment. Extra segment is 00. Now if I write an ES out here, right, if I have to write ES here, then this 11 will become 00, and since in this example it is DS out here, so it is 11, right? So 0001, so this actually this entire code becomes 0011, and then it becomes 1110. So 1110 is E, and 0011 is 3. So that's why I get this. So this is the prefix, right? Now next comes the this is the format for this is the standard format, right? So opcode. So these tables I had discussed in my earlier class. So I'm just put the snapshot of the relevant things. Okay, this entire table is available in our previous few lectures, right? So so first one is the opcode, which is the move instruction. Here we are moving from register to memory, right? So register to memory, and also it is an 16-bit data, right? So so register to memory for move register to memory is what? This is the code, right? 100010, right? From register to memory to register. Okay, so this is the code. So that code we get. So this entire table is available. You can refer to the previous lecture sites, right? This is direction, right? Now in this case, from register to memory we are writing. So this is the direction, right? You could have from a memory to register also, right? In that case D will be 1, but in this case it is from a register to memory. This is the direction of the flow of the data, and that's why this D comes to be 0. This is word, right? Since it is DX means it is a word. It is not a it consists of 2 bytes, 16-bit information, and hence W becomes 1. And this the mod 10, right? and mod is 10 stands for memory mode with 16-bit displacement, right? So I showed you a table of mod also, if you could refer the previous lecture. In for what are the four 00, what does 00, 01, 10 and 11 stands for. So you could refer to that previous lecture in mod data. So 10 stands for memory with 16-bit displacement. Here we have a 16-bit displacement, right? And that is the reason we are going to write it as 10. And then this is the register, right? Register is DX register, right? From where the data, and DX again for these registers also, these codes. This is snapshot from the big table, right? 010 stands for DX, so that is where it has come from. 110 again, 110 stands for, right, BP plus 16-bit. Again, for this table is also given to you in the previous I think lecture number 6, you could refer to that. 110 stands for BP plus 16-bit displacement. So this 110 comes. So once you have written 110 here, obviously the microprocessor would expect, okay, a 16-bit information in the next two uh, in the next two nibbles, right? So first you place the lower nibble and then the higher, okay? So this 4 5 comes here, and 2 3 comes here. So this is the opcode which is for this particular instruction. So this particular example, in this particular example, probably it doesn't make sense by writing DS here, right? Because default also it will take DS, but otherwise you could write ES, CS or SS also, right? Accordingly, here this here, right? No, sorry, this 3E will get accordingly amended. Okay, this 001 remains the same, 110 remains same. In between, okay, these two bits accordingly will get changed. Okay, so this is known as segment override. Okay, now coming to input output. Right, so this is the 8086. We will learn this block diagram in detail in when we talk about memory organization subsequently, but let me just give you a rough idea out here so that you understand the how in and out commands work. Okay, so what 8080 does is, it doesn't have separate address lines and data lines. They are in fact multiplexed. Okay, so there are a total 20 pins. Okay, out of the 20 pins, 20, all 20 of them are used generally for memory addressing, whereas 8086 is a maximum 16-bit processor, so it only 16 lines are used for data transfer. So the 16 lines are actually multiplexed. Multiplexed means time multiplexed. Okay, so at any given point, the same lines are either used as memory lines or they are used as data lines. So how does this work is, first suppose I have to get fetch some data from the memory, so the address is put here. Okay, 20 all the 20 lines are used, and that address is put here. Okay, that address is put here, and then what happens after that? Okay, now the address latch enable signal goes high. Okay, now what happens is, whatever was the address there, okay, this address is coming here also. So that address line gets latched here. Okay, now this becomes free, this line becomes free. Okay, so this address latch goes high, so now this address lines, this yellow lines, in this the address will be available. Okay, now this has become free, right? Once this has become free, now data can be placed here. Okay, so I have a latch, so this latch basically stores the address lines. Okay, so once the address line is placed, latch signal goes high, then the address comes here. So the same address lines will be available here. Now this is free for data transfer. Okay, now these address lines are placed here. Okay, now 8086, the memory is divided into two banks. Okay, one is known as the odd bank. We have a 20 megabit, right, a total memory, out of which half of it, 1 megabit, sorry, 1 mega byte memory. This is an 8-bit okay bank. Okay, this is this bit, right, it is a one word. This is the second word, and here there are 512 kilo by kilo lines, okay, and each line it's an 8-bit information, right? They are all, these are, you can consider that there are 512k lines, and in each line there are 8 columns. So an 8-bit information is available here, 8-bit information is available here. So when I select place some address, okay, depending on the least significant bit, okay, least significant bit will be available on address line A0, okay. So A0 either odd bank or the even bank. If the least significant bit is 0, odd bank will be selected. Since it's a digital data, it can be A0 can be either 0 or 1, right? So if it is 0, this will be selected. If it is 1, this will be selected, right? This chip will be selected. So somebody has to tell whether, right, this is to be selected. So that function is done by this a chip select chip, okay. So if you see in the chip select, let me this A0 information is also coming to this chip select. So if A is 0, obviously this chip will be selected, and A0 is 1, this chip will be selected. We are just talking about the memory occasion, okay. So obviously, and we also learned that, right, 8086, suppose I am writing a move, right, AL, and I am giving some memory address, okay, then 8-bit no, one 8-bit information will be brought. But if I write an instructions of right, if I write an instruction something like, right, move AX, that means now here 2 bytes of information will be fetched from the memory, right? So in that case this is only, right, only single excuse me, right, this is only an 8-bit, right, and this is also 8-bit, but if I write an instruction of move, right, AX, right, and then I specify some memory address, then the 16-bit data has to come, because this is AX, not AL or AH, right? In that case, two, right, suppose if I write here 1000, so some memory location, this is just the offset, so some memory location with ends with 0, this 8-bit information will be here, and the next memory location also, from there also data needs to. So when I write some instruction like this, the CPU also sends an information that now we are talking about an 16-bit information. So this bus high enable signal also goes high, okay, and hence both the chips will be simultaneously selected, okay, and hence you have an 16-bit data coming here, okay. All these things in detail will be explained in the memory location, okay. So this is how data comes from the memory, right. So however, when I write an instruction of in and out, okay, this is what we said, right, this is move instruction, okay. Move always brings data from the memory or within registers, but the moment I write instructions starting from in and out, okay, it means it is going to get data from a port, okay. So that it does, port could be anything, right, it could be a mouse, it could be an keyboard, it could be a printer, right, anything. So input output devices, okay. So for input output devices I write in and out, okay. So in and out means, in means it is going to get a data from a port, okay. Out means it is going to put a data into the port, okay. So this is how. So the moment I write in and out, okay, what happens is this chip select signals, okay, because you see here, this is when the memory signal, when I am writing move instruction, the memory signal will be high, okay. When I am writing in out instructions, that memory signal will be 0, and both these chip select lines will be 0. So these memories won't get activated, Okay, now what happens, since this memory input output pin which is coming from the microprocessor is 0, that means right now what address I am placing out here, that doesn't refer to the memory, but that address is corresponding to the input output port. Okay, so accordingly this input, and also when I write in, it means I am reading an information. So that signal also will be given here. Okay, a read and write signal, right? So in means I am reading it, so this read signal will go 0 because this is a read bar. So that will generate input read signal. Okay, input read signal IOR, and similarly if I write an out command, okay, then it will generate an input output out signal. So these signals will go and activate some, there will be some port here, right? So there will be an address decoder for the port also. So from these address lines, okay, these address lines, it will select the corresponding port. Okay, and that port will get connected to the address line. Okay, so that's how this works. Now so I have input output instructions, right? Here I don't have to specify, okay, the register, okay, because always the input, when I'm writing an in instruction, data will be brought either to AL register or AX register. If the port is an 8-bit port, so I will have to write in AL, and then I will have to specify the port from where the data needs to be. If it is an I can't bring data to AH. Okay, so I can write either in AL or in AH, AX. AX is when the input and output port, the port is of an 16-bit. Okay, so either the printer, mouse, it can be a 16-bit or it can be a 8-bit. If it is 8-bit, then I can get that information into AL register, and if it is an 16-bit, then I can get it into AX. No other data cannot be transferred from the ports to any other register other than AL and AX. Okay, so EAX is for 80386. Okay, similarly for the out. So we'll see some examples, it will be clear, right? So in transfers a byte or a word, okay, into the AL or AX register. Okay, now when I write an in, it can be two ways I can write, right? The first one is I can write an in, and then I can write the port number. Okay, so when I write the port number, right, this is an 8-bit, right, the syntax is 8-bit, right? So this is an 8-bit. So a total number of ports, okay, which can be connected in this particular, if I write here, is total number of ports which I can is 2 to the power of 8, right, which comes out to be 256. So from 0 to 255 ports can be addressed like this. Okay, so apart from 1K 1 MB memory, you can also connect parallelly 256 ports, right, into 8086, right? Also other than this, right, instead of addressing it like this, I can also write like this, in AXS DX. Okay, then the address of the port will be computed with the contents of the DX register. Okay, now DX is again an 16-bit register, right? So 2 to the power of 16. So these many ports can be connected, actually speaking. Okay, so this is the total number of ports apart from the memory. Okay, 1 MB memory, these many ports can be connected to 8086, right? Now no other register can be used along with the in command. Okay, now so when I write this, right, this is the machine code for it, right? You write like this, and then the port number, right? Otherwise for DX register, since no other register, you don't have to specify this. Okay, now if you see here, this 111 means 10 means, okay, that means it is an in operation, right? and from a port number requires to be specified. But here if you see here, there is a one out here. In this it is, it is already right, it is known that information has to come from the D. It is implied. Okay, so this is an here you don't have to specify the port number. So this is the machine code for these two instructions. Okay, in the next slide things will be even more clear. Similarly for out, okay, you can write an out instruction. That means whatever data is there in the AL register, okay, or AX register, okay, that will be sent to the port number, right, in this port. Okay, so depending on whether this port is an 8-bit, then it obviously, if it is an 8-bit, this will become AL, and if this port is an 16-bit, it will become AX. So this, whether it is AL or AX, will be decided by the port, the kind of port which you have used. Okay, so that's it. So let's see an example here, right? So here, now what happens is, if I write in, okay, AL, right, 19H. So this is the port, okay, this is the port. This is just the offset, okay, offset, okay, offset address, right? Obviously the address will be calculated DS into 10H plus the offset. So this is the offset address of the port. Okay, so this will it will physical address will be calculated, and from that port this address will be. Now this port is an 8-bit port, and hence I write AL. Now this port can be an 16-bit port. So accordingly, I have to write here AX. Now I can write this AL into DX also. In this case, DX, the contents of the port address will be given with by the contents of DX. Right, here it is an 16-bit port, and hence it is. Similarly out. So these are the port numbers which are given here. Right, so these are the port numbers, and here also, right, you can give the out instructions. So from AL this data will be pushed here, okay, into these ports. So these are the way you can read and write data from the ports, right? So there's so this is what we learned till now, right? And this is the memory, right? Parallelly you could have and ports connected, right? Suppose for this, obviously you will require an additional hardware, okay, which will generate, like this additional hardware will be required to generate an input output, right? And then you will require an one more decoder from this, so from these address lines to select that particular port. Okay, so some additional lines will be required. This is only giving a signal that it is an input output read operation or a write operation, but you will require a decoder from that address to select that part. That decoder action is generally done within this RAM, right, here for the memory. But for the input output ports, there won't be any decoder, right, within an input output port. So you need to have one more decoder block also to select the appropriate port as given by the address line, right? So that is required. And now suppose for some application there are some memory, all the memory we are not using, right? So in that case we can assign these memory, right, locations for as ports. Okay, and then we can use the same instructions and move instructions, obviously, right? So what happens is once that particular address is there, obviously you will require that decoder, but you don't require these IOR signals at all, because it is that port is so this memory instead of this memory, right, and you could have for example, okay, instead of, you just remove this memory bank, this complete memory bank, and you can probably use a smaller memory bank here, and rest of the address you can connect the same in the memory bank itself. Instead of memory bank, you could connect IO, okay, input output bands. So you can address them, only difference is you can address these IOs through your normal memory addressing commands, okay. So little bit of a hardware requirement is not there, right. So in case your IO, yeah, like for a certain memory, right, instead of the signal going to a memory, it is going to IO, okay. So I can still use the move command itself, okay. That is the advantage. So little bit of hardware required will be lesser, okay. But here, so this is a most ideal way of doing it, using IO ports and not disturbing the memory decoders, and you have a separate decoder. So little bit of extra hardware is required. So this is known as isolated versus memory mapped. Memory mapped means this, okay. If it is memory mapped, then you got to use the move instructions only to fetch the data, okay. So now after that we are going to see some more move data transfer instructions known as LEA, LDS, LES, LFS, LGS, and LSS. So these will be clear from examples. So let me take up an example. Okay. Now the first here it is load effective address BX 1234. Okay. So what it does is, uh, from the source, what is the offset address? Now in this particular case, this offset address is 1234. So this will be stored into BX. Like, so what is the difference between move BX 1234 here, right? So when I write move 1234X here, the content, this offset address, okay, plus DS into 10 plus this offset address, some memory location address will be computed, and the contents of that memory location would be brought into MOVX. Whereas here it is not going to fetch any data, only this offset address corresponding to what is reflected here comes here, okay. So this is something like a move BX and then 1234, okay. If I just write this also, does the same thing, okay. Now why this is there, like for example, if you take a more complex example here. Now if I write LEAX BP plus SI plus AX, so this offset address will be computed, and that finally that offset whatever is there, right, that would come here, okay. And since this offset is generally of 16 bit, you always have to specify a full register here, okay. Not you can't have BL or BH, okay. It has to be BX or AX. So this offset address is going to come here. Whereas if I write a move, this offset will be computed, and then from this offset, now the memory location will be computed, and from that memory location, right, the data will be fetched here to AX, okay. Here in this when I do LEA, only the right that offset value is brought into the AX register, right. Now okay, so this is what it does, okay. LEA transfers the offset of the source operand to the destination operation, okay. So a source operand must be a memory operand, and the destination has to be 16 bit, okay, general purpose register. Here it could be BX or AX or DX or CX, okay. So in one of these registers, that offset value will be brought. It does not affect, since it's a move instruction, it doesn't affect any uh, flags, okay. So this is the machine code. Now you might be wondering, what is the use of these things. See, sometimes when we write a high level program, suppose I want to say charge of an electron, okay. I want to charge of an electron, and I declare initially as a variable E, okay, is equal to whatever it is, 1/10 to the power of minus 19 coulombs or something, right. When I declare this, okay, what it does, what the compiler does is, in some memory location, right, the value of E is fed, okay. Now every time in the program, whenever I write, okay, now compute the charge Q, total number of electrons into charge of a single electron. So this value of E, whenever the program encounters E, right, now it has to go and fetch this value of the right, this value from some memory location, right. So when I say this variable E in my program, when I write variable E, what it does is, okay, this value of E is put here, right, and this memory location, okay, this particular memory location is also stored, right, corresponding to. So whenever I call for E, right, the first and foremost thing is to get that memory location. So that memory location will be internally it would do, it will when I use this variable, it will get that this memory location into one of the registers, and subsequently because these are all complex instructions which can be 8086 can handle complex instructions, right? And subsequently it will break that first it will get that memory location corresponding to wherever this variable data has been stored into one of the registers, and then in the next step from that memory location that data will be fetched. Okay, so these are some of the applications of these instructions. Okay, and then you could also have an instruction known as an LDS. Okay, this is known as a load pointer using DS. Now here if you see here what happens is 32, it's a 32-bit data, okay, which will be brought from the source, right, and put into a destination operand. Okay, so you have to declare a source operand, right, and that source operand will point to some data which is 32-bit, right, and then that 32 bits will be brought, and then you have to specify an destination operand. Okay, suppose the destination operand I am calling, I am say declaring it as CX, right. So in CX obviously only 16-bit can be brought, right. So in the source operand, how do so source operand is suppose a memory location. You have specified a memory location. Okay, so so from that memory location, an 8-bit, first 8-bit, then the next 8-bit, then the next 8-bit, then the next 8-bit, right. Total source operand, suppose you are indicating towards one memory location. So this 4 starting from that memory, increasing 4 bytes has to be fetched and put into some place. Now that's what's that some place where this data needs to be put. So you need to specify the destination register. In the destination register, if I write CX, right, so only 2 bytes of information can come here. What about the rest 2 data? Rest 2 bytes will be put it into the DS register. Okay, so this is default, we can't change this. Okay, when I write LDS, so 2 data will be brought into the DS. So I have to specify this source and the destination. Okay, it will be clear in the example. Okay, so let me give an example, it will be clear. Suppose I write LDS BX. Okay, this is the offset address. Okay, let's forget about this for the time being, right. So now this is the memory location, right. So from this memory location, one byte of information is available in 5001, right. So from there it is getting it into the BX register. So this is BL register. The next significant bit from the next memory location, it will be brought to the BX register, right, and then the next memory location, okay, it will be brought here. So this data, this is the data which was available here, this is the data which is available here, data. So this data which is available in this memory location will be brought here, and the next data will be brought here, right. If you write LES, then instead of DS, in the ES register it will be brought. Okay, so that is the difference between LES and LDS. So this is how in one go, so in one operation, right, two data transfer, total 32 bits of information will come from the memory into these 2 registers. Okay, So this is another example out here, right? Now SI, right? Suppose this is one instruction, move SI word PTR A. Okay, this is not A is not the register A. Okay, A means this address. Okay, when I do that, if I write these instructions, okay, into the SI register, first these two data will be brought, and then I write move AX. Okay, because into DS I can't get data directly, right? So these two data first I have to bring it into AX, and then from AX I can transfer it to DX. Okay, so now these three instructions can be combined into a single instruction, right? Normally, so suppose I have to get these two data into SI, and if I have to get these two data into DS, I have to write three instructions. Okay, first I have to get these two into SI. Okay, that can be done in a single instruction, but to get some data into DS, first I have to fetch that data into AX, and then from AX, right, and then now I have to shift it to DS. But when I write an LDS, okay, so these three instructions is combined out here. Okay, so it is a different thing that, okay, this instruction actually when the microprocessor is doing the execution, it will do like this. Okay, so so when I say data cannot be written directly into DS, that is because of some hardware issues, the way the microprocessor has been made, right? So here also, okay, so it is just an instruction, a high level instruction which is given to you, so that as a programmer you don't have to write too many lines. Okay, but 8086 finally right, it will go back to this is actually a combination of these three instructions. Okay, while execution it might do like this, right? So however, such complex instructions are also available for you as a programmer. So if you can make use of these kind of commands also, right? This is LES. We saw the difference between LES and LDS is, only thing is instead of these two thing going into the DS register, it will go into the ES register. So that is LES. Okay, this is again example of the same thing. LES, you could refer to the PDF which I am going to upload, right? Then there are some flag register data transfer. Okay, so this is an LAHF, PUSHF, POPF. Okay, these are the four kinds of instructions which are available. So we'll take one at a time. So load into AH and a flag. Okay, this means, okay. So what it does is, okay, AH is what? AH is an 8-bit register, correct? So whereas the flag is an 16-bit register, correct? So if you see here, this is how the flag register. We learned about the flag register, right? So these are 8 bits, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So whatever is the contents from here to here, okay, that goes into the AH register. Okay, so you can probably you are doing some instructions and you want to preserve the status of the flag. Okay, so you can move the status of the flags into AH register and do some other computation, and later on, if required, now I want to get back that data of the flag register back into this register, into the flag register, that is permissible. Okay, now these data you can't do anything about it. Okay, you can manipulate the flag register data here. Only these flag register data, okay, these from CF, PF, this is the carry flag, parity flag, auxiliary. These flags we learned, right? So, zero flag and the sign flag. So, these flags, okay, this information can be loaded into AH register and it can be brought back also from the AH register. Okay, this flag information cannot be taken to any other register. Okay, it can be only brought to AH register. And similarly, if you want to put some specific data into this flag register, okay, before the initializing, suppose you want to initialize the flag register for certain purpose, then also you can put that data into the AH, and from AH you can bring it here, right? So this particular instruction gives you that option of reading the data from the flag register. And obviously there is no data here. Okay, so when you take it into the AH register, so some crab data will be available at this positions. Okay, they don't carry any meaning. Okay, so these are the flags, right? So direction flag, so these are the control flags. Okay, this we cannot because they have got specific functions. The program, so the 8086 instruction set doesn't allow you to modify these. Okay, this is the direction flag and interrupt flag and the trap flag. Okay, so they are used for a specific purpose, and that is the reason that when we learnt about flags, we learnt about that. So these flags can't be manipulated. Okay, so now similarly I can have a store, right? So a store, what it does, like I said, load, what it does, from the flag it is put into the AH register, and from the AH register so if I have to initialize the flag, I can do that, or temporarily I have taken some data from the flag register to the AH register, and from AH you want to put it into some memory also, you can put it there, and subsequently again you want to bring back the original data into the flag register. You can again from AH you can from that memory you can get to AH, and then from AH you can get it back here. Okay, so this is what the SAHF stands for, right? From 386 onwards there are certain more instructions. So I am sharing the PPT, you could just go through that, and so 386 we won't because this course focuses on 8086, but there are a certain more instructions which are available in 386. Okay, so we'll stop it out here. In the next class, I think I missed out a few things. Let me go back here. Flag, PUSHF and POPF, F. Okay, I'll cover these two and then we'll do. So just to give you a hint, what it does is PUSHF is going to put the contents of the flag register into the stack. Okay, we learnt about the push and the pop, right? So this is going to, whatever is data in the flag register, that is going to put it, we talked about a well kind of thing, right? So into the stack it would go. When I say pop, it will bring back this data into the flag register. Okay, so this is nothing but push F, and pop F is nothing but, when I write push F, the contents of the flag, okay, will be pushed into the stack register. And then first, how does the PUSHF work? In the last class we discussed, right? When I write the push instruction, right, first of all, right, data will be put and the stack pointer will increase, right? And similarly, when I write the pop instruction, okay, the data will be brought out from there and the stack pointer decreases, right? Same thing happens here. So we have learned about push and pop, right, in the last class. So once I write F out here, okay, so what data needs to be pushed into the stack will be the flag register data. And when I say pop F, right, whatever is the stack, where should that data come? That should come into the flag register. Okay, so you could have a look at these two instructions also, right? It is the normal push operations. When I say push, right, when I write push and I specify some register, contents of that register is put into the stack. Here push F means the contents of the flag register will be put into the stack memory, right? Pop F means whatever is in the topmost available in the stack. Okay, the topmost data available in the stack, that will be brought again to the flag register. Okay, so this is what PUSHF and the POPF does. Okay, we'll stop it here. In the next class, and we will see few more data transfer instructions. Thanks a lot.